Recording in progress.
A very good morning to everyone present. My name is Shalini Dasgupta and today I will be presenting MSC-derived exosome-impregnated scaffold for developing vascularized graft development in perfusable lab-on-chip systems. Now before we begin, we would like to discuss what is the requirement for developing such a graft. Now vascularization is a very pertinent process, but no one has been able to develop consistent and reliable vasculature for large constructs and artificial organs. As of 2024, complete regenerative vascularization requires what is required for over 1 million people requiring urgent transplants. Over the 53% of the currently available commercial grafts will fail due to insufficient endothelialization. This is because they focus on surface healing but cannot support deep tissue injuries, and the current accepted gold standard, which is autografts and allografts, will be in short supply. Now, endothelial cells are often seeded upon these grafts, but they are short-lived, they cannot outlast 3 passages, and they have MHC2 markers, thus causing immunogenic issues. Now, in order to solve this above issue, one alternative is to use natural biocompatible polymers combined with vitamins and exosomes to be utilized to promote vascularization by transitioning stem cells which do not have any MHC markers towards an endothelial phenotype within the body. Now, what was the purpose of our study? Our purpose of the study was threefold: to develop a biocomposite bind using chitosan, collagen, fibrinogen, and D3 and enriching it with stem cell-derived exosomes. Instead of using expensive growth factors, we would seed stem cells on the surface of the scaffold to transition towards an endothelial phenotype and cause vascularization, and we would evaluate this vascularization in dynamic blood flow conditions. Now, before we added exosomes, we needed to see which exosome would be the best fit for it. So we evaluated the periodontal stem cell exosomes, which is known for having increased amount of VEGF, with DPSC, another potent source of exosomes, with fibroblast exosomes. After identifying and quantifying them using CD9, we evaluated their protein content and RNA content, where we saw PDLSC had much higher concentration as compared to the rest of the other exosomes. We also did FESCM study, where we saw all exosomes had spherical uniform morphology of size 150 to 200 nanometer, and based upon the overall results, we saw that PDLSC would be a good choice to be added in the biobank. After adding it in the biobank, we printed out our scaffolds and compared to our already established controls, which was CCF, chitosan, collagen, fibrinogen, and CCF-D3, which is just the composition without the exosome. There we saw that both in terms of degradation and swelling, our scaffold performed within the limits expected for a biocompatible scaffold to be implanted in vivo. Then we also did antibacterial studies, where we saw, in contrast to the first unit and the second unit, it had a median range indicating some antibacterial property. However, in MTT, it had comparative increase in compared to CCF-D3 and C3F. Now we chose CCF-D3 exo to be 3D printed in a Y-shaped channel, and which we implanted in a perfusable lab-on-chip system. Then in our transcriptomic analysis, we saw when we compared our lab-on-chip dynamic system for the CCF-D3 exo in a static versus dynamic condition, we saw that all the angiogenic systems, which is all the angiogenic genes, VEGFA, VEGFR1 and 1, and the endothelial genes, CD34, CD31 and IL6 were overexpressed, while the suppressor gene TGF-beta was underexpressed in dynamic as compared to that of static. When we did immunofluorescence studies, we saw that in DAPI, VEGFR1 and VEGFA over 21 days, vascular-like structures, jewel formation, cell aggregation, like to form capillary-like structures were observed with high expression of all these above genes. And also for the 2 other genes, for 7-day study, where we studied alpha, SM and effectin, both required for wound healing as well as vascular network formation, were also overexpressed in the dynamic condition as compared to that of the static condition. Thus, what were we able to prove? That PDLSC exosome was a good choice for exosome to be infused in the biobank, that the overall combined scaffold could promote antibacterial properties and increase both the biophysical capability as well as the biocompatibility of the scaffolds, and it could be utilized as a perfusable reactor system in a dynamic condition. What is our future work? In that is to optimize the printability of our biobank, to conduct in-depth study, and to provide long-term vasculation. The controls that we use, CCF and CCF-D3, these papers are added in our QR codes below, and my entire profile is given in the Google Scholar for any further questions. Thank you.